Welcome! In this session, we'll explore LeetCode problem number 697, degree of an array. This problem challenges us to find the smallest subarray that shares the same degree as the entire array. It's a great opportunity to practice using hash maps and analyzing subarrays efficiently. Let's dive in. In this problem, we are working with a non-empty array of non-negative integers called nums. The key concept here is the degree of the array, which is defined as the maximum frequency of any one element in the array. For example, if the number 2 appears 3 times in the array, and no other number appears more frequently, the degree of the array is 3. The goal is to find the length of the smallest contiguous subarray that has the same degree as the entire array. The input is a list of integers, where the length of the array can go up to 100,000, and each element is also within the range of 0 to 100,000. The output will be a single integer, representing the length of this smallest subarray. Let's look at some examples to better understand the problem. Consider the first example. The input array is 1, 2, 2, 3, 1. The degree of this array is 2, because the numbers 1 and 2 each appear twice, and no other number appears more frequently. To solve the problem, we need the shortest subarray that also has a degree of 2. In this case, the subarray 2, 2 satisfies the requirement, as it contains 2 occurrences of the number 2, which matches the degree of the entire array. The length of this subarray is 2, so the output is 2. Now let's examine another example with a longer array. In the second example, the input array is 1, 2, 2, 3, 1, 4, 2. The degree of the array is 3, because the number 2 appears 3 times, which is more frequent than any other number. Among all possible subarrays, the smallest one that also has a degree of 3 is 2, 2, 3, 1, 4, 2. This subarray includes 3 occurrences of the number 2, and its length is 6. Therefore, the output is 6. Lastly, let's consider one more example to reinforce this concept. In the third example, the input array is 1, 2, 1, 3, 1, 4, 1. The degree of the array is 4, as the number 1 appears 4 times. To match this degree, the smallest subarray that contains 4 occurrences of the number 1 is the entire array itself, 1, 2, 1, 3, 1, 4, 1. Since this subarray includes all elements of the input, its length is 7, and the output is 7. Finally, we should consider edge cases. For an array with a single element, such as 5, the degree is 1, and the subarray is simply the single element, with a length of 1. For an array with all unique elements, such as 1, 2, 3, 4, 5, the degree is also 1, and any single element subarray would satisfy the condition. In cases where multiple elements share the maximum frequency, we need to carefully identify the shortest subarray corresponding to the degree. For example, in 1, 2, 1, 3, 2, 3, 3, the degree is 3, and the smallest subarray with this degree is 3, 2, 3, 3, which has a length of 4. To solve the problem of finding the smallest contiguous subarray with the same degree as the entire array, we first need to understand what the degree of an array is. The degree is simply the maximum frequency of any single element within the array. A naive approach to solving this would involve considering every possible subarray, calculating its degree, and checking if it matches the degree of the original array. Once we identify the valid subarrays, we would then compare their lengths and return the smallest one. To implement this, we could use 2 nested loops to generate all subarrays and a hash map to count the frequency of elements within each subarray. However, this approach is extremely inefficient. With O, n squared, subarrays and O, n, time to determine the degree of each, the total complexity becomes O, n cubed. This makes it impractical for large inputs due to its computational expense, so we need to look for a better approach. A more efficient solution involves using a single pass with hash maps to gather all the information we need. Here's the intuition: instead of evaluating every subarray, we can focus on key details about the elements in the array. Specifically, we track 3 things: the frequency of each element to determine the degree of the array, the index of the first occurrence of each element, and the index of the last occurrence. The observations that guide this approach are straightforward. First, the degree of the array is determined entirely by the maximum frequency of any element. Second, to form the smallest subarray with this degree, we only need to consider elements with this maximum frequency. The length of such a subarray is simply the difference between the first and last occurrences of the element, plus 1. To implement this, we traverse the array once, updating frequency counts and recording the first and last indices for each element using hash maps. After determining the degree of the array, we iterate through the hash map to find the elements with this degree, calculate the subarray lengths, and return the smallest one. This approach is highly efficient, with a time complexity of O(n) for the traversal and an additional O(m) for processing the hash map, where m is the number of unique elements. In terms of space complexity, the optimized approach uses additional space for 3 hash maps, resulting in O(m) space, where m is the number of unique elements in the array. Given these trade-offs, the optimized approach using hash maps is the most suitable strategy for this problem. It dramatically reduces the time complexity from O(n) cubed in the brute force method to O(n), while the additional space usage remains manageable. By gathering all necessary information in a single traversal, we can calculate the smallest subarray length in constant time for each candidate element. When comparing approaches, the brute force method is conceptually simpler but computationally prohibitive for large inputs. Alternative strategies, such as sorting the array or using sliding windows, are less effective here because they cannot efficiently handle the subarray boundaries defined by the first and last occurrences of frequent elements. The hash map-based solution strikes the right balance between complexity and efficiency for this problem. The key insight, or the aha moment, is realizing that the problem can be simplified significantly by focusing only on the elements with the maximum frequency. Instead of checking every possible subarray, we reduce the scope to tracking the first and last positions of these elements. This observation allows us to avoid unnecessary computations and enables the optimized approach with hash maps. By reframing the problem in this way, we can solve it efficiently, both in terms of time and space, making this strategy not only elegant but also highly effective for the given constraints. The problem degree of an array asks us to find the smallest contiguous subarray whose degree matches the degree of the entire array. The degree of an array is defined as the maximum frequency of any single element within it. To solve this, we need to identify the degree of the array and then determine the smallest window that contains all occurrences of the elements contributing to this degree. To begin, we focus on the input and output requirements. The input is an array of integers, and the output is the length of the smallest subarray that matches the degree. Key information includes understanding that the degree comes from the highest frequency of any element. By tracking the first occurrence, last occurrence, and frequency of each element, we can efficiently calculate both the degree and the minimum subarray length. Now, we prepare the necessary data structures to support this process. To implement this solution, we use 3 dictionaries: frequency to track the frequency of each element, first to store the first occurrence index, and last to store the last occurrence index. These dictionaries allow us to quickly access the information needed to calculate the degree and subarray boundaries. We then traverse the array using a loop. For each element, if it's encountered for the first time, we record its index in the first dictionary. Regardless of whether it's new, we update its last occurrence in the last dictionary and increment its count in the frequency dictionary. Once this traversal is complete, the degree of the array can be determined by finding the maximum value in the frequency dictionary. Finally, we use this degree to identify all the elements contributing to it, and for each of these elements, calculate the length of their respective subarrays. By comparing these lengths, we can determine the smallest subarray. The process concludes with returning this minimum length as the result. The final step in our algorithm is returning the minimum length obtained after evaluating all the subarrays of interest. This approach is both clear and efficient because it ensures we consider only elements that contribute to the degree. Now, let's discuss some key insights that make this method optimal. First, using dictionaries ensures that lookups and updates are performed in constant time on average, which is crucial for maintaining efficiency. Additionally, calculating the degree and storing first and last occurrences in a single traversal eliminates redundant computations. This streamlined approach minimizes unnecessary loops and keeps the algorithm concise. We must also account for edge cases. For example, if the array contains only one element, the degree is 1, and the result is simply the length of the array, which is also 1. Similarly, if all elements are unique, the degree remains 1, and the output is any single element. When multiple elements share the same degree, we ensure that all such elements are considered to find the smallest subarray. To implement this algorithm effectively, we rely on three key data structures. The frequency dictionary stores the frequency of each element, which is essential for determining the degree of the array. The first dictionary records the first occurrence index of each element, and the last dictionary tracks the last occurrence index. Together, first and last enable us to calculate the size of the subarray for any given element in constant time. These data structures are chosen for their efficiency and allow us to seamlessly transition from determining the degree to identifying the smallest subarray. Now, let's evaluate the algorithm's complexity. The time complexity primarily comes from two steps: populating the dictionaries and calculating the minimum subarray length. Both of these steps involve a single traversal of the array, resulting in a time complexity of O(n). The space complexity of the algorithm is determined by the storage requirements for the three dictionaries: frequency, first, and last. Each of these dictionaries may store up to n entries, where n is the size of the input array. Therefore, the total space complexity is O(n). This trade-off in space allows us to achieve an optimal time complexity, as the use of dictionaries enables constant time lookups and updates. Now, let's look at the Python implementation of this approach. The code begins by importing the default dict class from the collections module, which simplifies the creation of the frequency dictionary. In the main function, we initialize frequency, first, and last. Then, using a single loop, we populate these dictionaries by updating the frequency, first occurrence, and last occurrence for each element. Once the dictionaries are complete, we calculate the degree of the array by finding the maximum value in frequency. With the degree identified, we proceed to find the smallest subarray that matches this degree. To do this, we iterate through the elements in the frequency dictionary. For each element whose frequency matches the degree, we calculate the length of its subarray using the formula last element, first element, plus 1. By comparing this length with the current minimum, we update the minimum length whenever a smaller subarray is found. After evaluating all relevant elements, the function returns the minimum length, which is the desired result. This implementation maintains clarity and modularity while achieving optimal performance. By combining efficient data structures, a streamlined traversal, and careful consideration of edge cases, the algorithm ensures correctness and handles input arrays of varying sizes effectively. Here, we begin by defining a class called solution and the method findShortestSubarray, which takes a list of integers, nums, as input. To solve this problem, we use three dictionaries: frequency to store the frequency of each element, first_POS to track the first occurrence of each element, and last_POS to store the last occurrence of each element. These dictionaries will help us efficiently calculate the properties of the array we need. Next, we iterate through the nums array using a for loop. For each number in the array, if it's not already in the frequency dictionary, we record its index in first_POS as its first appearance. Regardless of whether it's already been encountered, we update its last occurrence in last_POS and increment its frequency in frequency. By the end of this loop, we have a complete record of how often each number appears and the indices of its first and last appearances. From here, we calculate the degree of the array, which is the maximum value in the frequency dictionary. This represents the highest frequency of any single number in the array. We then initialize a variable min_length with a very large value to track the length of the shortest subarray that meets the degree condition. To find this shortest subarray, we iterate through each number in the frequency dictionary. If the frequency of a number matches the degree, we calculate the length of the subarray between its first and last occurrences. If this length is smaller than the current min_length, we update min_length with the new value. Finally, the function returns min_length, which holds the length of the shortest subarray that has the same degree as the original array. This is the result of our computation. By leveraging the dictionaries to store the frequency and positions of each number, we efficiently solve the problem in linear time, since each number is processed only once. This ensures that the solution is not only correct but also optimized for performance. Here, we start by importing the necessary Java utilities and defining the main solution class and method. The goal of this method is to find the length of the shortest contiguous subarray that has the same degree as the entire array. To achieve this, we use three hash maps, one to store the frequency of each element, another to record the first occurrence of each element, and a third to track the last occurrence. Next, we iterate through the input array using a for loop. For each element, we update its frequency in the frequency map. If it's the first time we're encountering this element, we record its index in the first pos map. Regardless, we update its last occurrence in the last pos map. After building these maps, we calculate the degree of the array by finding the maximum value in the frequency map. We then initialize a variable min length with a large value to keep track of the shortest subarray length that matches this degree. Now, we iterate over the entries in the frequency map to identify the elements with a frequency equal to the array's degree. For each of these elements, we calculate the length of the subarray that spans from its first occurrence to its last occurrence. This is done by subtracting the index of the first occurrence from the index of the last occurrence and adding 1. If this calculated length is smaller than the current min length, we update min length to reflect the shorter subarray. Finally, once we've checked all elements, we return min length, which represents the length of the shortest subarray with the same degree as the entire input array. Here, we start with the problem of finding the shortest subarray that shares the same degree as the input array. For the example array nums equals 1, 2, 2, 3, 1, we begin by initializing 3 dictionaries: frequency to track the frequency of each number, first_pos to record the first occurrence of each number, and last_pos to store the last occurrence. As we iterate through the array, we populate these dictionaries. For each number, we update its frequency in frequency, set its first occurrence in first_pos if it's not already recorded, and continuously update its last occurrence in last_pos. By the time we've processed the entire array, we calculate the degree of the array, which is the maximum frequency of any number. In this case, the degree is 2, as both 1 and 2 appear twice in the array. Now, we move on to finding the shortest subarray length that shares this degree. For each number with a frequency equal to the degree, we calculate the length of the subarray between its first and last positions. For number equals 1, with a frequency of 2, the subarray length is 4, 0 plus 1 equals 5. For number equals 2, also with a frequency of 2, the subarray length is 2, 1 plus 1 equals 2. We track the minimum of these lengths, updating min_length as we go. Numbers with frequencies less than the degree are ignored since they don't contribute to the result. After evaluating all relevant numbers, we find that the shortest subarray length for this example is 2. Moving to the next example, we repeat the process for nums equals 1, 2, 2, 3, 1, 4, 2, starting with the initialization of the same 3 dictionaries: frequency, first_pos, and last_pos. As we process the second example array nums equals 1, 2, 2, 3, 1, 4, 2, we populate the dictionaries step by step. For each index, we update the frequency of the current number in frequency, record its first occurrence in first_pos if it's not already present, and update its last occurrence in last_pos. For instance, at I equals 6 when processing number equals 2, its frequency becomes 3, its first position remains at index 1, and its last position is now index 6. Once all elements are processed, we calculate the degree of the array, which is the maximum frequency in frequency. Here, the degree is 3, as 2 appears 3 times, more frequently than any other number. With the degree determined, we calculate the shortest subarray length for this degree. For number equals 2, which has a frequency of 3, the subarray length is calculated as 6, 1 plus 1 equals 6. Since no other number matches the degree, the min_length remains 6. In the final example, nums equals 1, 2, 3, 4, 5, we initialize the dictionaries and find that every number has a frequency of 1. Since the degree is 1, each number forms its own subarray of length 1. Thus, the shortest subarray length is 1. This concludes the walkthrough of the solution, showing how we use dictionary tracking and simple calculations to efficiently solve the problem. To analyze the time complexity of our solution, let's break it down into steps. First, we have the initial pass through the array where we populate 3 dictionaries: frequency, first_pos, and last_pos. During this step, we traverse the input array nums once, and for each element, we perform dictionary operations such as insertion, lookup, and update. These operations are efficient, with an average case time complexity of 1, thanks to the underlying hash table implementation. Since we process each of the n elements in the array exactly once, the time complexity of this step is O(n). Next, we compute the degree of the array, which involves finding the maximum value in the frequency dictionary. Even in the worst case, where all elements in the array are unique, the dictionary will contain at most n keys. Finding the maximum value in this dictionary takes O(n) time. Together, these two steps contribute O(n) plus O(n) to the total time complexity. Now, moving to the second pass, we calculate the minimum subarray length for elements that have a frequency equal to the degree of the array. To do this, we iterate over all items in the frequency dictionary, which contains at most n entries. For each element, we calculate the subarray length using the formula last_POS number, first_POS number, plus 1. Since each of these operations takes O(1) time, the total time complexity for this step is O(n). Combining all these steps, the overall time complexity of our solution becomes O(n) plus O(n) plus O(n), which simplifies to O(n). Turning to space complexity, the main contributors are the three dictionaries: frequency, first_POS, and last_POS. Each dictionary can store up to n entries in the worst case, where all elements in the array are distinct. This means the space required for these dictionaries is O(n). Additionally, we use a few auxiliary variables like degree, min_length, and loop counters, but these require only O(1) space. Therefore, the total space complexity is O(n). Thus, the space complexity of the solution is O(n), primarily due to the dictionaries. To better understand the efficiency of this approach, let's compare it with a brute force method. A naive solution would involve iterating over all possible subarrays to check their degree, which would require time complexity ranging from O(n²) to O(n³), depending on how the subarrays are generated and processed. The brute force method does not use additional data structures, so its space complexity is O(1). However, our optimized approach significantly improves the time complexity to O(n) by leveraging dictionaries to efficiently track frequencies and positions. While this increases the space complexity to O(n), the trade-off is worthwhile given the dramatic reduction in runtime. This demonstrates how the optimized solution strikes a balance between time and space efficiency for this problem. Finally, let's evaluate the algorithm under different scenarios. In the best case, the input array contains only one unique element. Here, the solution processes the array in O(n) time, and the dictionaries require minimal space, so the space complexity is effectively O(1). In the average case, the array contains some repeated elements, leading to moderately filled dictionaries. Even so, the time complexity remains O(n), and the space complexity is O(n). In the worst case, where all elements in the array are unique, the dictionaries grow to hold n entries. Despite this, the algorithm still runs in O(n) time with O(n) space complexity. To mathematically validate the time complexity, the first loop iterates n times, with each dictionary operation taking O(1), resulting in O(n). The second loop processes at most n distinct elements, adding another O(n). Combining these gives a total time complexity of O(n). With the dictionary storing at most n entries, the space complexity is O(n). Overall, this algorithm is optimal for the problem, achieving linear time and space complexity. When solving this problem, there are a few common mistakes to watch out for. First, you might forget to track all the necessary information. For example, simply counting the frequency of elements is not enough, you also need to know the indices of their first and last occurrences. Without these, you can't determine the smallest subarray that matches the degree of the array. Another mistake is relying on nested loops to calculate subarray lengths. This leads to an inefficient O(n²) time complexity, which can be too slow for larger inputs. Finally, some may assume that the degree of the array corresponds to just one element, but multiple elements can share the same degree. It's important to evaluate all of these candidates to ensure you find the smallest subarray that satisfies the condition. Now, let's consider additional pitfalls. One of these is the incorrect handling of ties. For elements with the same degree, you have to carefully compare their subarray lengths to ensure you're returning the smallest one. Failing to do so can lead to incorrect results. Another frequent oversight is neglecting to test edge cases. For instance, arrays where all elements are identical, arrays with completely distinct elements, or even very small arrays can expose flaws in your approach. Ignoring these cases may result in assumptions that don't hold up under certain conditions, leading to unexpected errors during testing or in interviews. This problem also has valuable insights for technical interviews. A key takeaway is that it combines frequency counting using hash maps with range tracking, and efficiency lies in managing both within a single pass. Recognizing this pattern and interplay of array traversal and hash map usage is essential, as interviewers often assess your ability to balance time and space complexity. Your goal should be to achieve O(n) time complexity, and you should be ready to explain why approaches like nested loops or redundant passes are less efficient. Additionally, always clarify edge cases with the interviewer, such as whether arrays are guaranteed to be non-empty or if multiple elements can share the degree. As you explain your solution, explicitly describe the role of each hash map, such as tracking frequencies, first occurrences, and last occurrences. Clear communication of your thought process is just as critical as the solution itself. You can also deepen your understanding by exploring related problems. For example, LeetCode problem 1-2 sum involves using hash maps to track indices efficiently. Another is LeetCode 325, maximum size subarray sum equals k, which also requires finding subarrays with specific properties using hash maps. Similarly, LeetCode 560, subarray sum equals k, focuses on prefix sums and efficient subarray calculations. Lastly, LeetCode 209, minimum size subarray sum, has a comparable goal of minimizing subarray length while meeting a condition. These problems share overlapping concepts, and practicing them can help strengthen your ability to identify patterns and optimize solutions in similar scenarios. Lastly, let's discuss alternative approaches to solving this problem. The brute force approach involves iterating through all possible subarrays and calculating the degree for each. While simple to understand, this method is highly inefficient, with a time complexity of O(n) squared or even O(n) cubed, making it impractical for larger arrays. A more efficient option is the two-pass hash map approach. In the first pass, you record the frequency, first occurrence, and last occurrence of each element. Then, in the second pass, you identify elements with the maximum frequency and calculate their subarray lengths. This achieves O(n) time complexity but requires two traversals of the array. The optimal solution is a single-pass hash map approach, where you simultaneously track frequency, first occurrence, and last occurrence during one traversal. This method is both time and space efficient, with O(n) complexity, and is often the preferred solution in interviews despite being slightly more challenging to implement. Great job! To summarize, we effectively used hash maps to solve the problem by tracking frequency and indices, achieving an O(n) time complexity. Remember, this approach is particularly useful for problems involving subarrays and frequency analysis. Thanks again for joining, and be sure to stay connected for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!